Okay, let's start with today's lecture. Before we introduce more security protocols, I think it's important to recap the security primitives and what are the security services these primitives provide when we talk about security protocols. The reason is there are many security protocols, and the specifications of these protocols are quite different from each other, but they share some common principles. So it's important that we understand the common principle. Then it will be, I think it will be more easy for you to follow these security protocols. So that's why I think we need to recap a little bit. So first, for security attributes, regarding security primitives, there are several attributes it can protect. And the first one, confidentiality. The second one, integrity. I have to mute you all. Okay. And then we have this certainly authenticity and the long repudiation. Somehow this long repudiation and the authenticity, they share some common feature, because regarding long authenticity, it means especially for two communication parties, then the receiver is able to verify the identity of the sender. And in this case, based on authenticity, then the sender cannot at later time deny some message or some data it has sent out to the receiver because of this origin authenticity. So first, for confidentiality, we use encryption ciphers to provide confidentiality. And for performance, so we mostly use symmetric ciphers to provide confidentiality. Symmetric ciphers. We mentioned two common standards. First one is AES. The other one, the first one is DES. The other one is AES. And for most of the security protocols, they use AES as a common practice. And for integrity, then it uses message authentication code. And for specific primitives, then so far we can only focus on what is called HMAC. By the way, do you remember what HMAC stands for? Can any of you give me an answer? What HMAC stands for? I see you might already forget it. So a message authentication code is used for, good. It's used for verify the integrity of a message. But how can we design these algorithms there's one common or design principle is to use hash functions which are proven or which are widely used for security reason. Then these hash functions can be input with some extra secret key together with the data. Then it achieves the goal of having a strong message authentication code. And this type of message authentication code algorithms is termed as hash-based MAC, so short for HMAC. So it's quite natural, right? We have hash functions, and the only difference between hash functions and the message and the MAC is hash functions does not involve secret key, but for MAC we need secret key that is shared between the sender and the receiver. And to make it simple, why don't we just use hash functions to build up a secure message authentication code algorithm? Then it comes this HMAC. Now, let's look at authenticity to provide the or to ensure the identity of the sender. Now, in this case, we use public key cryptography. More precisely, we use digital signature. We have learned one public key algorithm, RSA, and which can be used for signing on some data, and then to generate the signature. And in assignment 1, you have already done like how to generate the signature with RSA and how to verify the signature. But here I again ask you one question. Do you remember how we combine primitives to have an efficient digital signature? If we have an RSA, then for functionality, it's enough to have a secure digital signature. To have more efficient process of signing and verification, then what else we need to input or to introduce into this process? Do you remember? No, yeah, I'm not surprised. In fact, because most of these public key cryptography schemes are based on some hard mathematical problems. So that you can imagine that this process involves many mathematical calculations. So it's computationally heavy. And it leads to the fact that all the existing public key algorithms, they are around 1,000 times slower than symmetric ciphers. And to overcome this kind of performance issue, then a common practice is to introduce hash functions into this signature process. So if we have some data and we want to efficiently sign on this data, then what we do is we first apply hash functions on the data to calculate its hash value, and then we use RSA or other public key algorithms to sign on the hash code of the original data. Then we get very short plain text for the signature. Then it's much more efficient than directly sign on the original data. That's the idea. So we use hash function plus, let's say, RSA. And since the security of RSA is well recognized, then if a sender send out some message signed by RSA, then this sender cannot deny it has sent out this message, because the other parties in the network know the public key of this sender, and they can easily verify the data, the signature is generated by the sender, and there's no way to deny it. So that's the general process of these security attributes provided by some cryptographic primitives. Before I continue, is there any question about this general process? Nope, that's good. Okay, in this process, I have intentionally ignore some part. That's how we share the public key. And we have mentioned in previous lecture that we have two types of way to sharing public key. Each of them are based on some public key certificate. And in the secure web browsing and many other practices, the public key certificate that is issued by some certificate authority is widely used. So that is so-called X.50 line public key certificate. And the idea is that, so here we have this communication between Alice and Bob via an insecure communication channel, let's say the internet. And sometimes, of course, we can directly, like Alice send a message to Bob, said, hey, Bob, this is my public key, I'm Alice. That's very simple. And Bob can also say, okay, I received your public key, and here is my public key to Alice. It seems it's fine, but the problem is if we have an attacker, let's see, Chow. He also sends a message to Bob claiming that, hey, Bob, this is Alice, and this is my public key. And also, meanwhile, Charlie sends another message to Alice claiming that, hi, Alice, I have received your public key, and this is Bob, and this is my public key. So this type of attack can cause some problem that Alice and Bob do not realize there's a middleman between them, that the middleman can intercept all the traffic. And to prevent this type of attack, which is so-called man-in-the-middle attack, then we need to have extra security mechanisms on protecting the public key of each communicating parties. And this, let's see, I write this is man in the middle. Then it comes to the kind of architecture of how the public key of loads in networks are managed by this public key certificate. Alice and Bob. Then we have this certificate authority. This certificate is considered as a trustable third party by Alice and Bob. And Alice will register her public key at the certificate authority. Like pub Alice. And Bob will also register his public key at the certificate authority. Well, for end users or for a party, maybe it's not that convenient to generate the public key and private key by themselves. Then certificate authority can help them. So on the other hand, so certificate, the CA can generate this public key for Alice and also public key for Bob, but the certificate authority maintains this public key. Then the next time, and when Alice wants to send some data to Bob to have secure communication, Alice will send the public key. And let's see here, we have certificate. C, certificate. I directly write A. It means the certificate of the Alice public key. And it will also send back a certificate for Bob. Then what Alice wants to show itself is Alice, then it will send the certificate to Bob. When Bob receives this certificate, Bob will check the signature on the certificate, which is signed by the certificate authority. And Bob is able to verify whether the signature is validate or not. If it's validate, then Bob accepts that public key is indeed the public key of Alice. Likewise, Bob will also send his certificate to Alice. This certificate has a signature by the certificate authority, and Alice will verify the signature. If it's validated, then this public key will be deemed as Bob's truly public key. So that's the process of this certificate issuing public keys to two communication parties. You may wonder why Alice or Bob trust this CA. Well, at a small scale, and if there's an authority that normally Alice and Bob has some interaction or have some business with, then they have certain trust in the CA. So they trust, as also they have the public key of the CA already. Then in this scenario, it's acceptable, it's already fine. At a larger scale, then maybe Alice and Bob has no idea what this CA is. Then they need to check the public key certificate of the CA itself. It might be signed by another CA. CA0, let's say, which has more authority for Alice and Bob. And if they verify the signature from CA0 on CA is validate, then they believe, okay, that the CA's public key is valid, and then the Alice and Bob's, like the other party's public key, is valid. So you see, this is a chain of verifying the public key of certain party. CA stands for certificate authority. This is a very brief kind of introduction about how the public key is shared among communicating parties in the internet. Today we will have lectures on TLS and SSL and also SSH. And basically they use this idea, and they also have some other security features to protect confidentiality and integrity. Before I continue, I would like to know whether you have some question regarding how the public key certificate is managed and is verified and is shared among communicating parties. No question, that's good. Maybe we can directly look at the certificate to see what it looks like. I remember I have shown to you before, but still, it's not bad. We can share one more time. So, for example, if I came to my email at UIB, then this web email.uib, then you see this padlock. And if you click on it, then you have this, okay, certificate, and then you have mentioned valid. And if I further click on it, I'll get more information. So first, let's look at this. So if we want to have a certificate, you can imagine what are the information we would like to have in the certificate. So here it's my browser is checking the certificate, public key certificate of the university, UIB. Then in the certificate, it should contain like who has this public key, which is called the subject of the certificate. And what is the public key? And then who issued this public key, right? These three fundamental elements in a certificate. It's pretty much like after you finish your bachelor, then you get a diploma on a bachelor degree. Then it will contain this information, and this certificate is for some students, like here, Alessandro, and then this student, and also it will mention the content of this certificate. It's maybe, okay, a bachelor degree on computer science, or maybe on data security. And then at the bottom, it will provide this university information, and also the stamp, sometimes the signature by the rector. And mostly, it will also contain the timestamp when this certificate is issued. That's for the certificate in the real world. And for some type of certificate, they has there's a validation time limit. If you attend some type of like CISP for the security certificate for security professionals, then after they got this certificate, but the certificate is not valid for all the future. It's only valid for maybe 3 years or 5 years, then it needs to be updated. And for the public key certificate, it's the same. It has a certain time of this validation period. In fact, there's a lot more other fields in public key certificate. Then let's take a closer look at what a public key certificate contains. And there's one standard called X.50 line, which is widely used in the internet. Can you see it clearly? Do I need to, maybe I can make it larger. So let's look at this. And first, the information, or we have this subject name. That's about who hold this public key certificate. And it provides basic information. And here the organization and this common name of this certificate. And then it gives the issuer name information. Who issued this public key certificate? So then it's normally it's a certificate authority. Here we have this certificate authority called CA shortly. And the information, okay, is this organization who has kind of certain authority to issue public key certificate for University of Bergen. And we have this basic information. And also for the certificate itself, then it needs some ID, right? So here we have this serial number that's basically as an ID for the certificate. And also there's different versions of the public key certificate. So in this certificate, the version is 3. So it's X.50 line version 3. And then we would wonder, okay, this public key is signed by another CA. Then what is the signature? And what is the algorithm used for the signature generation? Then here you find this information. So the signature algorithm is used SHA-256 as a function, as a hash function, and also use RSA to sign on the public key certificate. And then it comes this valid time period. It's valid from December 2019 till December 2021, this time period. After this validation period expires, then if the university pays for this public certificate to renew it, then it will get a new validation time. Then we also would like to know, okay, then we have this certificate. What is the content? What is the information of the public key for University of Bergen? Then here we have this information. So when we talk about public key, we would need to know what is algorithm used for the public key. Here then it's RSA, and the public key here it's in hexadecimal form. Then this is a public key for RSA for University of Bergen. And if you remember, then this is the big integer n, that is the product of 2 primes, P and Q. So the public key is n. And also, if you remember, another parameter in the public key is encryption key, this E. Here, this is exponent. This is exponent E. And since it's 250 bytes, so the key size of the public key is 2048 bits. And here, it also mentions what are the key this key can be used for. It can be used for encrypt. It can be used to verify it's a signature. It can be used to wrap some key information. Also, it can be used to derive some key. Then this part is for the public key information. And then we also need to know what is the signature for this public key, which is generated by the issuer here, this CA. Then it has this signature information. And for the other part, there are some extension field to provide more information about this certificate. So for our purpose, we only need to focus on these fundamental elements in a public key certificate. Then you may wonder, I have this public key certificate for University of Bergen, and I have seen the signature of the signature from the CA from Amsterdam. This signature from this organization. But how can I verify this signature? And to verify the validation of this signature, then we need, in fact, my browser needs to know what is the public key of this CA. Then if I can get the public key of the CA, then I can use the public key to verify the signature by this CA. Then how can I get its public key of the CA? So then I need to check the public key certificate of this CA. Now you see I click this public key certificate. Now I change it to this one, the CA's public key certificate. Then I see, the subject here is this CA. And now we see the issuer is another party, another CA. It's here. And it's digitcertificate.com, this organization. In fact, it's quite widely used. Then we have the similar information. What is the signature algorithm and the validation period, and also the public key information, and in the end, the signature on this public key certificate. Then how can we verify it, this signature? Then we need to load the public key of this CA which signs on this public key certificate, right? And we can go further, like here. Then we see, the holder of this public key is this organization, and the issuer of this public key is this organization. So now you see it's very interesting. This organization, it belongs its public key to the world, and then it signs on this public key by itself. So this type of CA who is entitled to sign on its public key itself is called root CA. And in the internet, nowadays, there are, I think, less than 10 well-recognized or well-accepted root CA. I think most of them are in US. So then if we don't have other choices to to trust on the CA. Basically, they are the early players in this business and when the internet was invented. So then we pretty much we rely on it. And that's this process. Is there any question regarding the public key certificate here? It's very important to understand the whole logic about the public key certificate. And you might get a question on this public key certificate in your exam. Good. It seems there's no question about the public key certificate. This is an X.50 line. Okay, I got a question from Neil. So basically, if a website has a valid certificate, it's protected from man-in-the-middle attacks. Yes, I could say so. I mean, in this general discussion, yeah, we assume that this valid public key certificate is enough to prevent man-in-the-middle attack. Provided that the root CA is trustable. It's not compromised, not hacked. But that's a rather unlikely to take place. Any other question regarding the public key certificate? Okay, then we can have a 15-minute break and we continue our lecture. So welcome back to our lecture. Now let's move on to our introduction on the transport layer security or secure layer, secure shell, secure socket layer, this SSL. There's some history about the SSL and the TLS. I will very briefly introduce them. In the beginning, SSL was developed by Netscape for web browsing, and it's not open source. After a while, the community feels like it's really necessary. It feels the dire need to have this type of extra layer of security protection for web traffic. Then they introduced this TLS by this organization IETF. At that time, the SSL was updated to version 3. So it's natural that TLS use most of the content in SSL version 3 with slight adjustment for itself. That's a TLS 1.0, that version. And then it started to be deployed in the internet by many companies and vendors. After a while, this version 1.0 was found some security weakness. And there are some serious attack on version 1.0. And it updated to version 1.1 and then later version 1.2. And I think last year or maybe 2 years ago, they introduced the TLS version 1.3, which is significantly updated. Previously, there's some security issues, then they just kind of patch the issue in this protocol. And after a while, then this this protocol was updated significantly. Now, if we compare the version 1.3 and 1.2, there's a lot of difference. I will introduce, in this lecture, I will introduce SSL version 3. Since we will have 143, this applied cryptography, and in that lecture, I will look into TLS version 1.3, the latest security protocol for our web browsing. So let's look at this SSL. It is composed of several protocols, in fact, 4 protocols. And most important protocol is this SSL record protocol. That's how the data is sent through this record protocol. And for this protocol to work, to function properly, then there's some preparation needed in the context. And also there's some adjustment on the protocols. Then there are 3 additional protocol. One is this handshake protocol. It's used to exchange the secret keys between a web browser to a web server. And in some cases, maybe the cipher suite need to be changed. Then they will have this SSL change cipher specification protocol. And in some cases, if a certificate of a web server is invalid, and also maybe some other type of issues, then there's SSL alert protocol to alert to each party, especially to the web browser, that there's something insecure features in the previous setting. They need to improve on it, or they need to replace it with more secure setting or parameters. That's the basic functionalities of these protocols. For you, it's very important to know that this record protocol is the primary protocol which provides confidentiality and the integrity of the message between the web browser and the web server. Another important protocol is this handshake protocol. It is used to authenticate each party. Like, it enables the web browser to authenticate the web server. Likewise, it also enables the web server to authenticate the web browser after the connection is established. And also it enables these 2 parties to negotiate the parameters, to negotiate the cipher suite, and so on and so forth. These other 2 protocol is the change cipher and also alert protocol. That's what I mentioned, to have some adjustment in the process. I think I can skip this connection and the sessions. In general, it's the SSL will start a session with the web browser will start a session with a web server. Then after the session is established, there will be many subsequent connections between the web server and the web browser. So these connections will be using the same parameters that is established via the initial session. That's the idea. So one session contains many subsequent connections between the SSL client and SSL server. So let's take a look at this record protocol operation. Suppose there are some data to be protected from the up layer, let's say HTTP data. On the first, this data will be divided into fragments. And for the protocol, it will contains information about the maximum fragment size. And it will divide the application data to the fragment, the acceptable fragments. And in some cases, these fragments will be compressed by a function. And then there will be a message authentication code algorithm applied on this compressed data. Then it adds this MAC code, or we say MAC tag in the end. Then after this step, the whole data here, it's original is compressed application data, and also the MAC will be encrypted. Now we have the ciphertext for the first fragment of the application data. Then in the end, there will be some necessary header information append to this ciphertext. That's the structure of the payload of the record protocol. Here is there's some more specific information about this fragmentation and compress. So first, normally they choose this maximum fragment size as 16,384 bytes. It's quite big. Then the compression process, MAC process, and encryption process, I already introduced. And also then the header of the SSL record, like here, SSL record header, it contains several fields. First, the content type, like what's the type of the payload for this record. It might be some higher layer protocol, like the other three protocol, and handshake protocol, or like change cipher spec protocol, or alert protocol, or it could be the application data from the up layer. Then it contains the version number of this SSL, and also if it's compressed, then it gives some information about the size of the compressed data. So in general, the record format is like this. So this is the data, original data. Then here we have the MAC, and it's encrypted. But remember that this encryption keeps the size of the data, the same as the original data. Here it provides some extra information, its content type, and sometimes because there are several versions, then which version would be majority used. Then we have the major version and the minor version. And also it provides the size of this data. To be more specific, there's some extra information about this, the change cipher spec, several these protocols. That this part is inside in the payload. For having this encryption and message authentication algorithm, then simply we would need to think, okay, what are the ciphers we use? What are the message authentication algorithm we use? Okay, that's the first question we would like to know, right? And then we would like to know how the keys between the web browser and the web server is managed. I mean, how the key is generated, how the key is shared. And that's what we care about in this context. And all these things are handled by the handshake protocol. This SSL handshake protocol, it allows the client and the server to authenticate each other, to negotiate the encryption and MAC algorithms, to exchange keys. That's the major functionality of the handshake protocol. And since it's not necessarily simple, it has to go through several phases. And these phases are, in the beginning, this hello request. Then normally we can skip this one. Then we have this client hello, server hello, then send the public key certificate from the server to the web browser. And sometimes maybe the web browser needs to send the public key certificate of itself to the server. But in most of the cases, it's not necessary to have the public key certificate of a web browser. And then we have this verification process to verify whether the certificate provided by the web server is valid or not. After this is done, then based on the agreed key exchange algorithm in the cipher suites, then we will have this client key exchange and the server key exchange information. After that, then the preparation is done. Then the server and the web browser at that stage will be able to send, to encrypt it, to first they have shared a key, then they will be able to do encryption and to run the message authentication algorithm on the application data. So let's take a slightly closer look at these phases. So when we start this SSL, this connect session between the server and the client, so client send a client hello message. It provides many information. We will look at it with Wireshark. And then server hello replies. Then mostly the server needs to provide its public key certificate. And also it might provide extra key exchange parameters for key exchange, especially if they use Diffie-Hellman key exchange. This part, this certificate request is optional. And after that, the server is done. If the client is requested for this certificate, it will reply the certificate to the server. And sometimes it might need to change the cipher specific for the together with the server. Then if everything is fine, then it's finished. So basically, after the handshake protocol, the server and the client has agreed on how to exchange the secret keys, how to generate the key, the secret key for encryption and for the MAC algorithm, and also which of the message authentication algorithm and the symmetric ciphers will be used for providing integrity and the confidentiality of the application data. That's the process. In fact, the key generation process is quite complicated. It's used a similar idea as this PDKT, what's this? PBKDF. this password-based key derivation function. Here, but since there's low password, but the generation of the key is quite similar as there. After the web client, after the web browser agreed on the key exchange scheme with the web server, then they already share some basic information, including the exchange key. This key is called this pre-master key. And then this pre-master key will be used to generate what is called master secret key or master key. You see, you have this input, this pre-master key, and then some extra. Now here we have a SHA and also then pre-master key. This is pretty much like how the HMAC works. Then this process will be repeated, but only with several parameters are changed, like here. The first one is A, then the double B, and then triple C here. And for the other information here is this some information about the server, some information about the client. In fact, it includes the timestamp of this session and the session ID, and also some extra information. Then with this master key, it is denoted as KM. This master secret will be used as an input to generate what is so-called key block, generate a long key block. And this key block, the first, it will choose like if they decide to have AES 128 for encryption, then they will take like the first 128 bit from the key block as the secret key used for AES encryption. And then later, if they use a MAC, suppose the key size is 256, then they will take the next 256 bit from the key block and use it for the MAC algorithm. That's how it works. Before I continue, is there any question about this process? This SSL is compared to TLS is relatively simple, and you can get the general idea how it works. Is any question? No? Okay. Then let's look at HTTPS to see how SSL is embedded into HTTP. Since I haven't introduced HTTP to you, so here it's necessary to just briefly introduce it. So HTTPS stands for HTTP over SSL or TLS. Then you can easily see this S from the address bar in your web browser. And with is HTTPS, so it used the port number 443. Normally HTTP use the port number 80. What is encrypted in this HTTPS? In fact, if you consider the HTTP data, well, when I type something in the address bar, like the google.com or uib.no in the address bar, and while I click it, basically this is a HTTP request from my web browser. I want to get some objects in the web server, like uib.no. And this is application data. So then it means this information should be encrypted in SSL. So the data, all the data regarding HTTP will be encrypted by SSL before it sends out to the server. And also all the information from the server will be encrypted by SSL before it is sent back to the web browser. And as in the first lecture, we mentioned the server and the client, they validate each other or authenticate each other based on the public key certificate of the web server. And for client, since normally if we want to access some information, some assets in the web server, which is only valid for legitimate users, then the client needs to provide credential. That's what we experienced every day, right? And let's look at, let's take a quick look at the Wireshark to capture some HTTP traffic. I captured it before since I want to save some time, then I directly look at it. Here, in fact, this is to make the traffic less messy. And I directly use a command like wget, then use like webmail.uib.no. Then I capture all the traffic. Here, in fact, when I sent this request, it's at the application layer, and before everything takes place, and there will be a handshake process for TCP connection that we mentioned in the firewall section. So here you see I use a wide connection, so it uses this IP version 6 instead of IP version 4 for communication. And this is my IP version 6 address. This is a destination IP version 6 address. And here, the first three, you see my terminal send a sync to this address. That's the university's email server. On here, the server replies sync and ARC, and then the client follows ARC. So these 3 steps is the handshake protocol. Yes, good point, Alexander. Is there any question for this process? If you don't have any question, then it's better to skip this. Okay, then I think we can skip this part. We can move on to the next part of the lecture. Next one is secure shell. This SSH. In the big picture, like if we have some clients, customers for a company, then they need to get some, they need to fetch some services or some objects from the web server. Then for secure communication, we use TLS, right? And for SSH, I believe most of you have used SSH before, right? And if you need to log in to a remote server, then you have to use SSH. And for the administrators or like web developers, if now they sit in front of their screen at office, then they need to manipulate and operate on the server. So then they use SSH to log in on this server. And also in this context, if the web developer or the administrator needs to upload some data to the server or to fetch some data or download some data from the server, then we have this scopy in the SSH. Or it can also use this SFTP, the Secure File Transfer Protocol, to exchange data between the administrator's computer or between maybe some other file-based computers. Then they have this exchange between these two machines. Here, we have this secure shell in the place to protect all the confidentiality and integrity between the traffic, for the traffic between the client and the server. Originally, people use a telnet and it has no security protection. Later on, this secure shell, SSH, was designed for secure remote login. And based on that, we can have this scopy. Let's take a look at the SSH. In the architecture itself, it's quite similar as SSL, but it has three components. One is this SSH transport layer protocol. Another is this SSH connection protocol and also authentication protocol. So for the authentication protocol, it is used to authenticate the client-side user to the server. And for the connection protocol, it's more like to take care of connection between the client and the server. So it involves this multiplexing process. And sometimes it involves this encrypted tunnel. We skip this. It's a little bit too much. And for this SSH transport layer protocol, it provides server authentication, confidentiality, and integrity. Sometimes it provides a compression, but it's not necessary. Let's look at these two sides authentication process. For server authentication, well, the server has the public key and private key pair, and it assumes that client loads this public key. Then for all the subscription traffic, and the server, for example, this key exchange, the server signs on the message with its private key. And for the client authentication, that's for us as end users, we use a lot. There are two types of authentication to authenticate clients for SSH login. One is called key-based. So the client generates public key and the private key pair, and then send the public key to the server. And after this is established, then for all subsequent login, then we just need to type in SSH and the server's IP address or domain name. Then we can automatically log in. Another type is password-based. Then client, normally the server will generate or create a user for this client. Then for the next time when this client wants to log in to the server, then we need to, okay, specify SSH, then the username at this server's IP address or server's domain name. Then we will need to provide a password. The password will be encrypted and sent to the SSH server. And if the password is validated, then the server will approve the login request by the client. These two types of authentication for client. Here, let's look at this key-based SSH authentication, which is rather convenient, in fact. So here we have, suppose we have 3 parties, server 1, server 2, and Alice. So after the initialization, then server 1 will like create the server 1 has the public key of Alice. So each of them, they have a pair of public key and private key. Like for Alice, like as a user, it has its own private key and public key. For the server, it has its own public key and private key. And for server 2, it's the same. And also to authenticate the client Alice here, the server needs to have the Alice public key. And also to authenticate the server 1, the user needs also to have the server 1's public key. Based on it, then if any subsequent traffic between Alice and the server, then server 1 here, then this public key will be used to verify the traffic, the signature on the traffic between them. Now, it's the same for between Alice and the server 2. So if server 2 wants to like log in to server 1, then again, server 2 needs to share its public key with server 1. And also it needs to get server 1's public key. So then it's like this process. Server 2 will maintain the public key of server 1. And also here, the public key of server 2 is sent to server 1. And after that, all the traffic between server 2 and server 1 will be rather similar to the traffic between Alice and server 1. And we can skip this. And for SSH, it's different from SSL, which use ISA to exchange keys between the client and the server mostly. But for SSH, they mostly use the Diffie-Hellman key exchange. Or after the key exchange, the new keys will be generated for encryption and for message authentication code. So then this key is key client to server, and again it's some hash function, and this key is the key has been shared or exchanged after the key exchange step between the client and the server. And it's this edge and also some session ID and some extra information. And this hash, again, it has a key involved. So it's 2 layers of hash functions to generate the key here. Here we have these ciphers. Then you see you have a 3DS CBC, you have AES, either 256 or 128, and with this CBC mode and other ciphers. For MAC algorithm, you use the SSH protocol, use HMAC. And we can skip the compression algorithm. In general, the payload is like this. We have some information, some data from the client to the server, then it will be compressed, and then it will be added some padding information and also some key information here. It's some parameters of the key, like extra information, or we can say it's a metadata of the public key. And also the sequence number for this payload, because it again, it will be divided into fragments. Then it will be this part will be encrypted and with ciphertext. Here, the MAC algorithm will take all and compute the MAC tag appended to the ciphertext. So you see, it's first, it's here it's encrypted, and here it's MAC, so it's encrypted and MAC. That's the format of the transport layer packet information. That's pretty much the specification of SSH protocol. I think you already see a lot of similarities between SSL and SSH, although there are also a lot of differences. Is any question? No question. Let's move on to the last part. It's about privacy in the internet. When are SSL used and when is SSH used? That's a good question. This slide explains the usage of these two protocols. So for end users like us, if we want to visit some websites to have secure communication, then TLS or SSL is used in this web browsing process. And for the web server itself, it needs to be accessed by its developers or by the administrators of an organization. Then they maintain the web server, and then they need to log into the web server. Although mostly it could be that they are in the internal network, which is supposed to be more secure, but also it would be useful that the administrator can log in to the server, like from home, with the internet, not the internal network. Then in this case, SSH is very useful, and I would say it's critical for this type of remote login. Is it clear, Jürgen? Okay, good. Now since you not already have a certain understanding about SSL, or let's say TLS, in the last few minutes, I would briefly introduce the privacy in the internet. That would be very useful for end users. And I know some of you already use the Tor browser. I will skip this introduction part. I will directly come to the privacy option. So basically, you want to have privacy in web browsing. It means that we want to hide our IP addresses from other parties, right? And here I have some. Let's look at this several of this figure. So here, this is a user, and here is a web server. And first, let's look at basic browsing with HTTP and also the firewall enabled. Now, in this case, if the user send a web request, HTTP request to the server, then it includes this source IP address, the destination IP address. So that's the user's IP address and the server's IP address, and also some HTTP request. It is sent and to the firewall and go through the intermediate loads here. And for the firewall, if you remember, then the firewall will check the source IP address and the destination IP address. So in this case, the firewall knows the user is sending some request to the web server. Not necessarily it will check the data, but it knows there's some traffic between the user and the server, since the firewall knows the IP address of both of them. And if there's no firewall, then it's fine. And yeah, we can remove this now. But as Jorgen asked, when this SSL is used. So for the end users here, we don't really want the firewalls to be able to see the data, because some of the firewalls, like the application proxy firewall, is able to see the data and even manipulate on the data. And the user don't want to the firewall to be able to see the content of the data. Then in this case, we use HTTPS. And then the data will be encrypted, but still the source IP address and the destination IP address will be seen by the firewall. So HTTPS do not protect the confidentiality of the request itself, but it does not provide any privacy protection against the firewall here. And here it's now how can we prevent the firewall to know the source IP address and the destination IP address? Especially, how can we prevent the firewall to fill out some HTTP request? Suppose you are still sitting in the student lab, you want to visit Facebook or Twitter, which is by default rejected by the firewall. Then how can you visit the Facebook web page? Then the web proxy comes into place. This is a process. In general, it's we have the user send out the request with IP address information, and the destination IP address is to the proxy, not to the server. If the proxy is not blocked by the firewall, then this request will be able to go through the firewall to the proxy. Then the proxy relay this request to the server. When it gets the information, then it will forward back the HTTP reply. But in this case, the IP packet contains the IP address information from the proxy, not the server. So that's how we can kind of bypass the firewall, right? And here we have, yeah, we can skip this. It's basically what I described. And also, for this case, it's the firewall cannot block the traffic between the user and the proxy if the proxy is not added into the block list in the firewall. But the data content could be seen by the firewall. To make it secure, then we would use HTTPS to send the traffic to the proxy. Now, in this case, the firewall cannot know the content of the HTTP request and the real destination of the request from the user. Yes, HTTPS provide integrity. I mean, that's still not enough. The reason is here the proxy knows the user. And then we have this virtual private network. It's another type of security protection. You know VPN. Yeah, let's just look at VPN. It's a functionality, and what's the difference between VPN and the proxy? In fact, here we have the proxy in between the user and the server. The proxy, normally we just look around what are the available proxies, and then we send some information via this proxy to the server. But these proxies are not necessarily trustable, and we don't want to use this proxy to log in to our bank, to log in to our maybe Facebook account, because this proxy could be able to steal our credentials for our precious account. And then we have this virtual private network, which is maintained by an organization for its employees. Now, in this case, the virtual VPN server can be regarded as more secure or more reliable or more trustable than a new proxy to the user. And in this case, with VPN, then the original data and also the original destination IP address will be encrypted by the VPN protocol. The firewall will be only see the destination IP address is the virtual net. Then it's after the VPN receives this request, it will decrypt it, get the original destination IP address, then it will forward this traffic to the web server. That's how it works. It's very useful when we travel around. Then we use VPN like with the university. Then if you want to log in to your online bank, like at the airport, and you use the Wi-Fi hotspot provided by some restaurants, but you don't really trust that hotspot, then it's good to use a VPN to connect to your online bank. Then you are better protected. Now, of course, together with HTTPS, it's be better. In the end, we have this onion routing, this Tor browser. In general, you can consider it as 3 layers of virtual private or 3 layers of web proxy servers. I see we are already running out of time, and I will skip this. I will explain this Tor browser next lecture. Okay, that's all for today's lecture.